The very first gauge I built in the pilots of Mythbusters was this kind of gauge. So I'm guessing this is a nice analog gauge that is actual.
You got it.
I shouldn't tip over the equipment. Hey everybody, Adam and Norm from Tested, and this is the Area 51, Alienware's flagship desktop gaming PC.
So Adam, in addition to having, of course, the latest system components from Intel and NVIDIA, Alienware engineered this system with a unique point of view when it comes to system cooling.
Yeah, there's long been a debate among PC builders about which method is best, a negative pressure design in which exhaust fans pull hot air out of a system, or a positive pressure design in which intake fans bring ambient air and push it into the system.
The Area 51, with the way its fans and components have been arranged, has been designed to maximize the benefits of positive air pressure, to a point where there aren't even exhaust fans on this, which is rare for a gaming PC.
And how do you prove that? Well, Alienware and Intel, the sponsors of this video, tested two Alienware's testing labs to see exactly how they prototyped this and how they validated their positive pressure airflow design. All right, Travis, tell me where we are. What is this room?
Well, welcome. This is our advanced thermal engineering lab where we do advanced testing on airflow and cooling. We cover everything from desktop products to other products that we can't talk about in particular. Sure. But it gives us really the capability to dig into the systems to know, are they doing what they're supposed to be doing? And can we basically achieve the cooling of the unit to hit the performance targets for our platforms?
So this is a room where you are stress testing the equipment to make sure it's performing as you want, or figuring out why it's not performing as you want.
You nailed it.
Okay, and this is the machine being tested right now.
You got it.
Tell me what the question is and how you're answering it.
Yep, so this is our cream of the crop desktop product that we sell for gaming. And in this particular case, performance really comes down to cooling capacity. Mm-hmm. What do we do? How do we get the energy that's going into the motherboard, the CPU, the GPU, out of the box as efficiently as possible to keep those gamers gaming and to ensure that they don't throttle or not have any frequency challenges on the system itself?
So the components in here are generating tons of heat because they're processing tons of data.
You got it.
Your guys' goal is to bring cold in there so it's working more efficiently.
You got it.
And I think everyone who's ever had one of these in their house knows the sound of computer fans, and you're also trying to reduce that as well.
You got it. So basically from the overall stack of what we're looking at doing is, hey, how do I cool it as efficiently as possible, as quiet as possible, and give that power availability to the other components of the system? And so from that, we do everything up front as far as layout of the system, cooling of the system. We size fans appropriately. And then at this stage, we are verifying all the work that has been previously done on projections to ensure we're hitting our targets.
Okay, so the engineers have designed a system. They have an idea of what it can do, and you're going to tell them whether they're crazy or right on the mark.
You got it. That's exactly what we're doing
today.
So
let's walk through the specific testing here. Yep. Why is this covered, and what is it looking at?
Great question. So this particular unit, if we open it up, you can see that just like any other desktop
ton of air is flowing out of here.
The layout of the system is critical to the overall cooling of the unit itself. And so this particular system has fans surrounding the entire periphery of the unit.
So fans here, fans down here.
You got it. So up top, we've got a couple 120s, 180s, and then we got the fans down here cooling the power supply. This approach from the math, the physics, basically minimizes any of the losses, and it gives us the capability to push all the airflow down the channel and actually pre-charge the GPU fan with pressure. In this sidewall, we have two tubes. These tubes are pitted tubes.
These are like what an airplane uses on the side to tell its airspeed.
Identical. If you look at the sensor itself, it has holes around the periphery of the rod.
Yeah.
It is managing static pressure and not dynamic. So a lot of people can tweak numbers by actually using velocity of air through the tube hole.
Right.
But since this is basically perpendicular to the flow path, it's just measuring pressure.
Okay.
And so this port gives us the capability to look at locations in the system to measure pressure in the system.
I don't think a lot of people realize, I mean, it's a natural extension, but I don't think a lot of people realize that a fan pushing air into a thing is actually creating a higher pressure in that thing. That's what you're monitoring.
You've got it. So basically electrical energy goes into a fan. It's a mechanical engine. It changes that electrical energy to pressure and volumetric flow rate. And what we're doing is we're measuring this to ensure, hey, do I have positive pressure? What's going on in the system?
Right.
Do I have the right flow?
And a high positive pressure means you're moving a lot of air, which means you're removing a lot of heat.
That's right. And the reality, the right answer to that is pressure doesn't cool, flow cools, but it gives us the optimization of where we put the flow within the system.
So you can move these into different locations
and you can measure
get different pressure differentials.
That's right. That's right.
Wow.
And so from this, the big 180s are basically flooding the internal chamber.
Right.
You get this coming out. Now, the back from this system itself, you can see the vent pattern. It also dictates pressure. And so it's almost like a throttling valve. So you can open and close it depending on how we designed this. And so it's important to manage that so you know the pressure is going where you want it to go.
I'm curious about why you don't just want as many holes as possible.
You can. So here's a couple issues. If we put holes down here, it's going to recirculate. So the exhaust is going to come out. It's going to come back in here. And you are then adding power back into the box.
Right.
That negates cooling, right? It's the worst thing you can do is when you have recirculation within a system. If you increase flow, let's say there wasn't recirculation and you added vent holes, it can help to a point. And so you have to ensure that, do I have the flow going where I want it to go? In this particular case, the radiator is up here with the cooling capacity of the system. This is the power supply, which is pulling in this direction. The main component we want to cool is the GPU, because this is being pre-cooled by the system fan. So all that pressure is actually helping the GPU fan by positively pushing into it.
So then if you had holes down here, that might lessen the amount.
It would bypass the flow.
Okay.
So really, you have to be really intelligent, and all this work by the engineers. We do computational fluid dynamics to look at the flow through every single region. But really in this case, and every case is different, it was ensuring that we had that flow going to the GPU in the right location. And because this is pushing through the radiator, we don't have to worry about the CPU cooling because it's all being pre-cooled from the air coming in from the top.
Gotcha. Oh my gosh. So this is the result of tons of simulations about airflow and cooling and heating.
3 months, 30 simulations, and I can tell you a ton of work. That's what goes up front.
What is happening at the output?
Yep. So if we close this back up, this is a flow bench. A flow bench follows Bernoulli's principle to basically use pressure, right, to determine how much flow is coming through it. So in this particular case, we have the PC completely ducted to this flow bench. The flow bench has a motor in the back that pulls on the system. So you've got pushing, you've got pulling, and at this interface, we are basically measuring the pressure to determine how much flow I'm getting out of the unit. So this first pressure transducer, it's a diaphragm, right? The diaphragm flexes with pressure. You get voltage output, and that's correlated. This pressure transducer manages the pressure across the unit. So this one here is right at this location. This is ambient. So you have a delta P from this spot to ambient, which tells you the pressure across this unit. Then there's a secondary pressure transducer, right? That's a diaphragm that is pushing across a nozzle. So the nozzle internal, if it's a 2-inch diameter nozzle, 1/2 rho V squared A, that gives you velocity based upon pressure delta P, right? So now you have velocity. You have area. I've got CFM, cubic feet per minute, right?
And you have the most accurate version of CFM that you could get because it's all controlled and contained.
We go down to the thousandths inch of water. In this particular scale, this is the hundredths inch of water.
Well, let's talk about inches of water, because I'm guessing this is a nice analog gauge that is actual.
You got it.
I shouldn't tip over the equipment.
I like
the
it
actual
now.
Inches of water.
You got it.
The very first gauge I built in the pilots of Mythbusters was this kind of gauge to do a pressure differential on a giant pane of glass.
You've got it. So basically this is old school, right? When they say inches of water, it's literally inches of water columns. So if you took a scale and you look at this, so you see this is basically a hundredth of an inch of water is each one of these ticks.
Will this work if we put this in there?
You can. So here, why don't you do it? Put it on the high side. So just right up top. Just push it down on that nozzle.
And so there's pressure coming out of this tube, and it is going to be, look at that. So this is just basically the old legacy equipment.
You got it.
And like those are up there the same kind of thing?
You got it. So if you look at it, you're measuring 0.017 inches of water. And you're 0.017 inches of water on this one. Now, if you hold this, I'll ramp up the fans and I'll show you what it'll do. So don't let that tip for me.
Well,
let's do this.
Oh yeah, look, it's climbing. 0.05. 0.1.
So this shows you, this is actually
the internal
you just turning
pressure.
up
the computer fans.
So I turned the fans up. So you are seeing the internal pressure of the system. So we have created a positive pressure on the unit. Now this isn't perfect. I'll have to seal it here in a second. But this shows you, hey, what we're doing, that positive pressure is basically creating a cavity to drive energy.
It strikes me that these readings also help you tell the engineers where to go look for the solution if something's not performing at optimal.
You
at the
got it.
optimal
So
rate.
in the simulation, like the CFD or FEA, if we had PQ curves, which we'll talk about in a bit.
Yeah.
So if I had a fan, right? So this front fan in particular, let me pull this out real quick so I don't drop this. This fan is going to have a performance. We on our labels basically show what they call the open flow, which is 152 CFM. As this fan rotates, basically it pushes air through the hub side.
And 150 cubic
Yep.
feet of that per
That's
minute.
right. So if I have predicted this thing should have a total 175 CFM at say 0.1 inches of water, and I know that this is off, then I can look at what fan isn't performing and go back to our design team and say, hey, let's look at changing the design and how it's done.
Travis, can we see an actual test?
Absolutely. Would love to show you.
Okay.
Okay, let me get behind you and I'm going to
All
change
right.
some velocities and we'll get this going. So in this particular case, we're going to start at the high end. We're going to
Okay.
put the fans on all full speed, right? And we're going to use the tool to calculate total CFM coming through the box in this particular case. From a tooling perspective, we have Alienware Command Center.
Yep, yep.
So we have full control of our fans
Wow.
from a product perspective. And so it makes it really nice from a test because you guys can repeat this testing wherever you want.
Right,
Customers
right.
can repeat it. Probably don't have the equipment, but you could absolutely do it. Now, in this particular case, we've got a couple things going on. The flow bench is not on yet, but the system is running. One of the tests I like to do at the very beginning is a smoke test.
Oh,
And so in this particular case, it's almost like a fogger at Halloween.
yeah.
So if you guys have these at home.
No, we have a bunch of these.
yeah.
We love this kind of.
And then basically you can look at the distribution of flow going across the radiator, and you can see where is flow coming within the system itself. So you can see a lot of flow is going through that core section, right?
Yeah.
Then you can come down through the bottom as well in the front and pull it in. This system, one thing to note, and we'll talk about this from an acoustics later, this gap was critical for acoustics. You talked about acoustics, but
Oh, really?
basically the fan has a noise. Think of it as like dropping a rock in a pool of water at a
Yeah.
lake. You ever see the waves that go out in the water? Acoustics is the same thing, right? It's a wave, it's a pressure wave. In this particular case, the noise is coming from the fan. It hits the front, and guess what? It goes this way.
And you're killing most of the sound
Noise,
that way.
right? So it was about, I
Amazing.
think if I remember correctly, it was about a 23% reduction in noise from this shape.
I would
what we've
imagine
done.
also, in addition to the shape, there could be material choices that would increase
There
that
can,
as well.
and additionally, like we talked about velocities,
Uh-huh.
this gap was critical. So when we designed
Oh,
this,
how big it is.
because
Oh,
if you
wow.
squeeze this too tight, you get frictional losses.
Right,
We talked
right.
about that. It's velocity squared.
It's working too
And
hard
so,
to pull
so
air
this
in.
particular case, there's very minimal pressure losses across the front of the unit. The flow bench. So as we talked about earlier, we've got a couple different situations. This pressure transducer, the diaphragm we talked about,
Yeah.
is measuring static pressure to ambient. So this port is open. So this is atmospheric
It's
pressure.
giving it the control.
And this is the pressure right at this port location.
Right.
So this will be the operating pressure of the system. This differential pressure transducer is used to measure velocity, which is flow. So when we talk about CFM, the amount of flow coming from the fans, this guy here is going to tell it to me
Copy.
based upon that pressure. Now, what we're going to do in this particular case, if I have the fan off, you can see we are operating at 0.112 inches of water. So
Yep.
that is the internal pressure at this location. You and I played with this earlier, but we'll show it again. But we can look at different ports. We can use the foam board to actually put different holes in different
Right,
locations.
right.
It gives us the capability to scale across the product to look at pressure. But similarly, you can get your analog gauge to do the same thing.
Wow.
So it's spot on when it's level. Now these gauges, old school, has to be level.
Oh, yeah,
And
yeah,
so you
yeah.
have to be,
Look at
you
that,
have to
of
be
course.
careful because you can throw it off if it's not level. So
Yeah.
it is important. But you can see how close these analog gauges are to the actual digital gauge.
Yeah.
0.113, and you are right in that same location.
Amazing.
Right? So this is your inches of water column. Now, what we're going to do is we're going to take the fan that's in the flow bench and pull on the unit to get this pressure to zero. When this pressure is zero, this pressure will tell me how much flow is coming out of this system.
Amazing.
Okay? So I'm going to crank it up. It's going to get a little loud.
Oh, no worries. I love a wind tunnel.
So you see pressures went down. It was 0.1. We're now
Yep.
0.02.
Yep.
Tell me when that gets down to zero. So there's a trim piece. It's basically a board.
Oh, almost there. 0.0. There you go.
right.
That's it.
It's not going to get better than that. So you're
Yep.
talking thousandths of an inch of water. We're at 4.23 inches of water across that 2-inch nozzle.
Okay, so what is the CFM that this was outputting?
172 CFM for this particular unit.
That's huge.
It's a lot.
Do you guys regularly try and overshoot what you need?
We do in this particular case. So in this case, we talked about the GPU and in particular the fans that they have and the PQ that they operate at. We are purposefully taking the energy from those fans and pushing it onto that blower to help give us that cooling capacity. Additionally, this was about flexibility. So this generation, we were looking to give that ability for customers to upgrade. You buy this chassis, it's fantastic. If I get a future motherboard, I maybe I'm going to pull it out and put a new motherboard in.
Right, and
You
it
can
may
do
be a
upgrades.
hotter motherboard,
Exactly.
and you want this to accommodate.
And so we have that capability.
Right,
There's another reason we do it, which we should talk more to, which I think you guys are going to talk to reliability later. We derate all those components on the motherboard. So every capacitor that stores energy, every FET that transitions, say, high voltage to low voltage to amperage for that CPU,
Each one of those is a heat source.
all those are derated too. So we have to, so if the spec on the cap, like is a 95C 2,000 hour cap, that's like only like 3 months. We run those capacitors at say 60C, you're going to get 10 years of life. So that's an example of the reason we also do this. If you buy something off the shelf, I don't believe they're doing those type of calculations.
Right.
And so that gives you the capability. We know it's going to have a 5-year to 10-year life. It gives us the warranty capability to sell to our customers, and you don't have to worry about it.
Right.
Like when we do these things. But that's the real reason. So the 172 CFM is probably a little bit overkill in this particular case, but it's about longevity.
Right.
What can we do to ensure that that part is going to live for a long
And
time?
not just longevity of the upgradability, but of all the components inside.
You got it.
Incredible.
That's primary.
That is thrilling. I love a wind tunnel test.
Yeah.
Travis, thank you so much for walking me through this. It is way more detailed than I thought it would be. It's incredible.
Thank you, Adam. Yeah, we love it. Love gaming, and hopefully our customers love it.
This is incredible.
Tim, Jonathan, I want to ask you guys about the design of this new Area 51. As designers, as engineers, you guys have this amazing job of coming up with how the components are laid out with the ability to go completely blue sky. So where does it start when you're designing a full tower ATX system?
It starts where it always starts, right? It's about performance, about power. It's about heat, right? It's about keeping those components as cool as possible. And there's a lot that goes into that. There's a lot that goes into ensuring that the airflow is right, ensuring that the performance is always exactly what our customers expect, what they demand. And just making sure that everything is as fine-tuned and lined up as possible.
So how much freedom do you guys have to design a system? I know there are components and partners you're working with, but give me a sense of the scope of the challenge here.
We'd start from scratch. If what we're looking for doesn't exist, then we'll design better performing components.
It's more than just
parallel.
designing a case.
It's more than just designing a case. And actually for existing components, we're always looking a few years out. Like this system, for example, is actually designed for stuff that doesn't even exist yet, for much higher wattage cards. When we first started this one, the 450 watt card didn't even exist. And we were designing for like a 900 watt and above.
As PC builders, you've seen the power requirements increase, right? Back when we were first building gaming PCs, 300 watts for the entire system might have been good enough. But when you started this, NVIDIA had cards that were taking up 300, 400 watts. You're talking about a 1,500 watt power supply here with cards that now are longer than a foot. Is that kind of where you start for like the volume and the dimensions of a case?
Yeah, actually, initially it was the graphics cards that defined the length, but looking to the future, we intentionally made the decision to support a 420 millimeter liquid cooling module, which didn't even really exist yet. There were some, but there were very few, and that defined the overall length, which gave us the space for longer cards in the future, which led to like the end holder, the adaptable end holder design that we have. There are many reasons that we don't have like fan ducts, air ducts, and stuff like that. And it made it really complicated to try to pressurize the graphics card. And one was from an accessibility standpoint. We've been doing research with Intel's accessible computing team and Southwest ADA in Houston, associated with a university and the medical center, for aging users and gamers with disabilities. So from an accessibility concern, we didn't want extra parts that were more difficult to use, to take out. It made it easier from a factory standpoint, field serviceability, customer accessibility.
Jonathan, I've heard in the past you talk about, with this, going back to some of the core philosophies of upgradability and serviceability and just letting the user think about things like the future. Can you talk about how those things are manifest in this design?
Well, yeah, I mean, we went back to standard ATX design, right? Motherboard, power supply. Even the liquid cooler on top, where it's how it's mounted, where it's mounted, the mechanicals behind that, easily accessible, easy to remove, easy to access.
You have one here. Can we take a look at that?
Yes, absolutely.
Yeah, so this is a custom radiator that you guys have spec'd out. You guys have different configurations for fans here.
That's right.
For flow. But Tim, you were saying like this size kind of determined your dimensions of this machine, and therefore how much volume you had and how much airflow you can push through it.
Absolutely, absolutely. And even on the thermal architecture and solution, we still have gaskets that block leakage and prevent recirculation internally. Everything was analyzed for over a year.
You have to think holistically, you have to factor in all these considerations and things that only you guys can do if you're designing it end to end, where you can talk to all your vendors and get things that are custom spec like this. Can we flip this around and take a look at the back? Because even the back of a system where I'm building it, I'm shoving cables around there because I don't want to see it necessarily through the door, but you're talking about like even placements of where your expandability can be. That's all very specific to this.
Yeah, so this is actually basically a thermal chamber itself. And we tested and simulated every possible location and configuration, literally hundreds of simulations.
How far do you go in terms of your prototyping? You do stuff in software with simulations, but when we're talking about the blue sky imagining of where a component can go, are there models that you mock up? Is it design blueprints? Like how far do you go with each possibility?
Sometimes it's models to get an idea of the general form factor. And it could be as simple as buying an existing chassis and getting out the Dremel, having the fun stuff.
Oh, wow.
You're cut it apart. Oh, yeah.
A lot of that.
That's the most fun, actually. So that's one of the really fun parts is.
And if you're going that far as to physicalize an idea, you're going to put it through some testing.
Absolutely.
So,
absolutely.
Some real,
Yeah, we do make a lot of physical mock-ups, a lot of physical prototypes. And those go through acoustic testing, shock and vibe, thermal testing, EMC, as well. So there are a lot of considerations, and this is the result of 1.5 to 2 years of many iterations of many different concepts.
But you're talking about considerations because it's considerations for people who are buying systems that ship to that you have then no control over. If I'm building a PC, it might just sit under my desk and I'm never moving it, but you're designing a chassis that has to support people maybe grabbing this and dragging it and lifting it. And so what type of validation do you do for just the integrity of the physical machine?
We have some very exhaustive shock and vibe specs to make sure that this passes. Anything that looks like it's a handle is going to be used as a handle.
Someone's going to carry it lifted that way.
Yeah, so we have very strict tests on how much weight this can support, which is far many more times than the system itself. These routing features are actually strengthening brackets.
Oh, okay.
Yeah, they're definitely double function. When we might not have them in the beginning, but after a ton of analysis, and we see this tray just bending like crazy.
Yeah.
We also have a large opening to access the CPU plate. We had to add this bracket to give the motherboard tray that rigidity that it needed again.
Do you guys consider the ATX form factor, the full tower form factor, a solved problem? I know the answer is probably no, but like what are the things that you're excited about, as this is an iteration of how you think about modern components and thinking about the future?
This is very, very future proof from our perspective. So we're excited for something out of the ordinary to come, for a 900 watt graphics card or just something crazy to come and be needed to fit in this chassis. And we're ready. We've done analysis for the stuff that you can't even think of that doesn't even exist yet. So it's exciting to see how this will be used in the coming generations.
Yeah, it's a very PC gaming philosophy because you know that's coming. You know at some point we're gonna want more power. It's gonna require more power, and it's really cool that you guys have thought about all that. Thank you both so much.
Absolutely.
Never look at a PC the same way again.
Is there like a back of the envelope equation for calculating proper CFM for gaming?
It's actually much simpler than you think it would be.
Really?
Yeah, power is directly related to airflow times the temperature delta of whatever I'm measuring. So this is the governing relationship. So if you talk about the details, basically the shorthand calculation is 1.75 times your power, N.
Times the amount of power that the power supply is delivering to the system.
So if you had a 1500 watt power supply, you just put 1500 into P.
Gotcha.
And it's going to give you airflow in CFM,
Cubic feet per minute,
times the delta T. So this is the temperature in minus the temperature out in degrees Celsius. So you do have power in watts, CFM of airflow, degrees C as far as the delta T. Let's say I want a 55 C exhaust temp. So in this particular case, I want to cool 1500 watts. It would be 1.75 times 1500 equals CFM times 55 degrees Celsius.
That's how much temperature you want to lower across the board.
Yep, that's the exhaust temperature coming out of the unit, minus, say, the local ambient. We typically design to 35 C. So you do 1.75 times 1500 divided by 20. It's 130 CFM.
Okay.
So that is what would be required for this delta T for 55 C exhaust, and you would need 130 CFM minimum.
That's so simple. So each value that is necessary for a different model requires an adjustment of all the other parameters.
You got it. Servers, right?
Yeah.
The same equation uses for servers. It can be used for power plants. It's the exact same calculation for everything. This relates power to airflow. That's it.
Super cool. I understood most of that. We want to thank Alienware and Intel for working with us on this video and giving us so much access.
And Alienware's engineers for inviting us into their lab so we could see how they test and iterate their design of the system.
If you have any more questions about Area 51, you can follow the links below.